Alright, and so in the last video we discussed iterated integrals as a result of Cavalier's principle and how we were slicing there. But in there we had a double integral, right? So why do we need a double integral? Well, okay, in that context, it might have made sense more generally, but let's assume for a moment that we're back in Calc 1 world and we're trying to think of, okay, well, we have Calc 1, and that was where we said, okay, we have to partition our region into intervals and find approximating rectangles. Well, how does that idea extend here? So again, if we have that same assumption where we have f of a function on a rectangle, we can say, okay, well, if we have a rectangle from from A to B, if you can imagine this, and then C to D as our bounds, okay, the idea of Riemann sums we can actually maybe try to do here. So what I would need to do is partition A to B into a certain number of intervals, okay, and we get a lot of them, right? So this would be A is equal to x naught, and then we get x1, x2, x3, so on and so forth, and then xn minus 1, and then xn, okay? And then similarly, C, we would have to partition that interval because we're on a rectangle, so we have to partition that. We would say that this is y naught, and then and then we have a few more and up to there. So then this would be y1, y2, y3, so on and so forth, up to yn minus 1, and then D would be yn. Okay, so then we would certainly proceed and kind of make a grid here. So I'm going to make my best straight lines that I can freehanded, and so on and so forth, and da-da-da. Okay, and then similarly I have to partition the y's. So if I look at, let's undo that. That was bad. If I partition the y's, okay, I get something that looks like this. Okay. So this, I would have to make a grid in essence of my rectangle, and then now I need to think, okay, well, this is just kind of the two-dimensional plot, but then remember, this is all underneath the surface that I'm looking at, and so let's say I'm looking at this lower left-hand box, and I'll color it so we can see. If I'm looking at that particular box, okay, now this is one particular region under the surface, right? But this entire region would extend up to underneath the function, or just on top of however we decide. And so the idea here is, if we're thinking back to Calc 1, okay, within each interval I took a test point. Well, which test point am I going to use? I have an entire little rectangular region. That usually we have to just pick something and go with it. And that's actually what we did in Calc 1. We either use the left, the right, or the midpoint. And so maybe I'm just going to use the midpoint here, and I'm going to call that C 1, 1. Okay, and then I would proceed to pick test points in each of these, and so on and so forth. And those would be the places where I make sure that when I extend this region up to my surface, that I get that point intersecting the surface. So really what we're saying geometrically is that each of these regions, when I extend them up, they create a box, okay? And so if I were to take each of these regions up and compute the total volume, the volume really is just the sum of the boxes, okay? And so if I look at the Riemann sum, okay, and I'm going to say the Riemann sum here, S, and this, well, yeah, I don't want to use R because that's the region, so we'll use S for now. It'll be the sum over all I and j starting at 1 and going to n. Okay, and so I do split them into the same number of regions, both in both directions just for ease. Otherwise, I would have a double sum, and that could be, well, interesting. But if I think about this, the width of each of these boxes that I'm extending up, that is, say, delta x, okay, because I've split it equally into some number of, I've split that that interval a to b into n intervals, all of equal length, okay, so there's that, and then the kind of the other dimension of this rectangular box would be, or this rectangular area would be delta y, okay, so delta x and delta y to get the area of this little region, and then to extend it up to that function, or up to the surface, that would be where the function comes into play, and this would be f of Cij for whichever one I'm in, okay, and that would just be the Riemann sum. Okay, so again, this first part gives kind of your height of your box, and then this gives you the area of the rectangle. Or if you want to think of it as the area of the face of the prism. Okay. All right, so that should be the Riemann sum. All right, and then previously in our last video on iterated integrals, we said f needs to be non-negative. If it's not, then it's just a signed sum of volume. So you can have negative volume and just know that it's below the x, or below a certain, or below the z-axis. Okay. All right. So then, really, what this gives us is that when we take the limit of the Riemann sum, that is denoted as just a limit, and then that gives us what we think of as the double integral. Okay, so that's how we define the double integral. So double integral over the region of f dot, or f dA is that, and then when we say that integral exists, we say the function is integrable. Okay, so the idea that we have to have this double integral existing is critical. How and when does it exist? Okay, so that's what we're going to start with in the next video.